Hello, all learners. In today's video, I would like to show you a simple case Bayesian network analysis. So this is a part of the causal analysis using R series. Okay. First, a few key points about Bayesian networks. So Bayesian networks are directed acyclic graphs, DAGs, okay, representing variables and their dependencies. Nodes represent variables, edges show conditional dependencies between them. Okay, so what this saying is Bayesian networks are DAGs, okay, and their nodes are random variables, and the edges are directional and showing the conditional dependencies among the random variables. Okay. So each node has a probability function based on its parent nodes. And they use the Bayes theorem to update probabilities with new evidence. And inferences computes unknown probabilities given observed data. And the acyclic structure enables efficient computation. And they are widely applied for reasoning and uncertainty in AI, bioinformatics, and decision making. Okay, so hope this is a very quick and brief review of Bayesian networks. So in this video, I'm going to show you probably a very, very simple example of how do you actually fit a Bayesian network model. Okay, so the R package we use is the Beaysian package. Assume we already installed it, so just load it in. And then we'll define the DAG structure as a model string. Okay. So we use this function model to network. You can see the syntax is model to network, parentheses, and double quotes. You got bracket A, bracket B, bracket C, given A, comma B here. Okay, so what this is setting up a Bayesian network model. So this tells you A and B are two parent nodes, okay? And they don't have any parents by themselves, okay? And then C is their child. So C conditioned on A and B, okay? And here A and B are independent of each other. So you have A, B, C. So you in the graph you just see an arrow from A to C, and another one is arrow is from B to C. Okay, so you define this Bayesian network structure by using model to network command, and you save the result in the DAG model. So since we're using like synthetic data, so I'm gonna just create a dummy data. So it's called a dummy data frame. It has A to be a factor. So it's a sample of yes or no, 100. Replace it with true. B is a factor, yes, no. And C is a factor. Okay. All right. So now we get a dummy data set. So if you are analyzing a real world data set, this would be your data set. Okay. This is your training data. Okay. So what you can do is you use the Beaysian.fit function in the Beaysian package, and you fit a model, say Beaysian.fit DAG underscore model. Remember, this DAG underscore model is the template. It's the Bayesian network we specified, but it's only a structure. Okay, it doesn't have any values, any numerical values, estimates in it. So it's just like a template. But we use this template. So this is the structure of the Bayesian network. And we're going to use the dummy underscore data as the training data. So the syntax is very simple, just Beaysian dot DAG underscore model, comma dummy underscore data. Okay. So we fit it, and it's a very quick, so we already fit it. And after we fit this model, now we have an estimate Bayesian network to start with. Okay. And what we can do is we can generate data samples from this fitted network. And what we can do, we can set random seed here. I usually use today's date, 11 November 10, 2025. So what we do is we can use RBN. So randomly sample from this Bayesian network using the fitted underscore BN as the original model, original network, and we sample 100 times. Okay, so we generate in the data, and then we generate like a sample size of 100, and then we fit the Bayesian network to the generate data using maximum likelihood estimation. So now we refit the model using the same Bayesian network structure, DAG and square model, but on the synthetic data generated, okay, the data. And we call it fitted underscore BN, and this is what it looks like. So it actually gave us the parameters of node A. It's a multinomial distribution, but it's actually we just only have two values, yes or no. Give you the conditional probability tables, and then you got the for the conditional probability table for C. This is more complicated. You get given A, you get a conditional probability table for C, and given B, you get a conditional probability table for C. Okay, so this is a fairly simple, but what I want to explain to you is what I just showed you is a foundational workflow for using Bayesian networks for reasoning and data simulation. So we did the minimal work. We didn't go further. Okay, but let's review the steps. Define the Bayesian network structure to specify the variable dependencies. That's the first step. Create sample categorical data, dummy data required for the parameter learning. In real-world application, this would be the real-world data, okay, the training data. And fit the network by estimating conditional probabilities from the data, and then generate new synthetic data consistent with the fitted model, and refit the network to the synthetic data to demonstrate the data updating. Okay, so you can also here, if you have new data coming in, you can use the fitted model on the new data, and that's kind of using the fitted Bayesian network on new data to get more updates. Okay, and then you can do this process illustrates moving from a qualitative graph to a quantitative probabilistic model. Okay. In practice, real data replace dummy data for meaningful model fitting, and repeated fits on generated data mainly help understand the model behavior or for demonstration. Okay. And we can do a lot more with this refitting the network on synthetic data. We can evaluate, for example, stability, robustness, and also we can use it for prediction if we have newly incoming data. Okay, but we're not doing any further analysis, so I just want to show you a very minimal kind of a workflow for fitting or using Bayesian networks. Thank you for watching, and please like our video, subscribe to our channel, and please feel free to ask questions and share this video with someone who may be interested in. Thank you very much.